Hello everyone, I am Federico Silvetti, a second-year PhD student from Rome Sapienza University. In this video poster, I will discuss high-energy resummation in multi-differential cross-section for heavy work production. This work was done in collaboration with my advisor Marco Bombini, and a publication is currently in preparation. First, let's start with some background on proton-initiated processes. As an example, consider photon-induced deep inelastic scattering. The QCD cross-section in orange is computed as a Mellin convolution of a coefficient function, highlighted in red, and a Parton distribution function, PDF in short, denoted in green. The overall cross-section depends on two variables, x, which controls the resolution of the proton probe, and q, the energy scale of the virtual photon. Now, the coefficient function can be computed in perturbation theory directly and encodes the scattering of the virtual photon with an elementary component of a proton, namely a quark or a gluon. Instead, the PDF represents the momentum distribution of said components, and it's a non-perturbative object. Only its energy scale dependence can be computed in perturbation theory via Altarelli-Parisi equations. Remarkably, the hadron level cross-section is both the result of QCD theory computation and an input, in the form of scattering measurements from experiments for the determination of PDFs. Since these are a large source of uncertainty in theoretical collider physics, there is always interest toward including novel data to further constrain them. Indeed, LHC provides a way to probe a region of X as low as 10 to the minus 6, beyond the reach of dataset inherited from previous colliders. However, in this kinematic region, QCD perturbation theory fails due to the appearance of large logarithms in the X variable, fittingly called small x logarithms. In order to restore predictivity and obtain accurate PDFs, these terms must be properly accounted for through resummed perturbation theory. Indeed, the plot on the left shows that fixed-order computations on their own fail to reproduce experimental evidence at small x. Thus, our motivation for small x resummation is enabling the use of a high-energy LHC data to place new constraints on PDFs. Before elucidating how resummation is performed, we can look at some features of these small x logarithms. First, it must be noted that logarithms of x are generated in perturbation theory in a single enhancement for both the D-glap splitting functions and the QCD coefficient function. In the former case, resummation is performed via the BFKL equation, and it is already known in literature as leading and subleading logarithmic order. In the latter case, instead, resummation is achieved by using a different factorization scheme with respect to the collinear one discussed before. So far, this technique has been proven only for leading logarithms. This means that only the first tower in the table below is resummed for all powers of alpha strong. In practice, the strategy is this. The hadron level cross-section is written as a Mellin convolution of an off-shell coefficient function and an off-shell PDF. Both depend on a new energy scale, kT, which quantifies the departure from the collinear factorization scheme. Of these two objects, the first one describes the scattering of the photon probe with an off-shell gluon, and it encodes all the process-dependent information. The latter is given, in turn, by a convolution of the collinear PDF and a suitable evolutor, which describes the conversion of a collinear parton into the off-shell gluon by repeated emission of T-channel gluons. This structure of stacked correction is, in fact, process-independent and has already been implemented in a robust numerical implementation in the reference below. Then, the resummed collinear coefficient function is obtained by comparing the two factorization theorems and cleverly rearranging the convolutions. Indeed, there are a lot of technical details regarding gauge choice and proper definition of KT factorization, which we cannot elucidate here and now. A more detailed picture is offered in the references below. In order to present our new result, we first return to collinear factorization. In presence of two initial state protons, the hadron level cross-section is still given by a convolution of two objects, this time a collinear coefficient function, denoted in red, and a parton luminosity, denoted in green. This Spartan luminosity is itself given by nothing more than the product of two PDFs corresponding to each proton Spartan. Notice that now the convolution symbol denotes a double Mellin Fourier transformation, as both a momentum fraction and a rapidity are necessary to describe the initial state at parton level. The other parameters are just a symmetrization of the DIS1s for the case of two protons. With this clarification out of the way, we can show that the off-shell factorization theorem still works like in the DIS case, provided that two PDF evolutors, one for each initial state particle, are introduced. Then, the resummed coefficient function can be again obtained by comparison. The equation in the lower box is our result, a reformulation for a resummed coefficient function fully differential in a final state invariant mass, transverse momentum, and rapidity. Heavy quark pair production was chosen as a practical application, as the LHC-7TV data includes accurate measurement for charmed mesons production for x as small as 10 to the minus 6. So the computation was carried out in two steps. First, the off-shell coefficient function was obtained by evaluating the three diagrams above with off-shell incoming gluons. Then, the resummed prediction was obtained by taking the convolutions with two evolutors as shown in the previous slide. Two different parameterizations for the final state were tested. First, the quark-antiquark pair kinematic, due to its simplicity, and then the single quark one, which has actual interest for phenomenology application. The main advantage of this approach is the ease in producing phenomenology predictions. For example, here are shown two numerical plots of the coefficient function over rapidity. The left one is differential in pairs center of mass energy, transverse momentum, and rapidity, of course, while the right one is integrated over transverse momentum. In conclusion, this work produced an expression for a small x resummed coefficient function fully differential in any combination of invariant mass, rapidity, and transverse momentum. Moreover, an application to heavy quark pair production has been numerically evaluated for single body and pair final state kinematics. As mentioned before, the natural prosecution of this work is a new resummed determination of PDFs, leveraging LHCb high-energy heavy meson production data. Another parallel avenue is to extend the resummation procedure for the coefficient function to next to leading logarithmic precision, thus matching what has already been done for Diglab splitting functions. This second endeavor is currently under study in collaboration with Anna Rinaudo, Simone Marzani and Giovanni Ridolfi from University of Genova, as well as Marco Bombini from INFN Rome section. I thank the organizers for hosting this video poster session and you for your attention.